Nice to meet you all again. So this class, what I planned, let us do. I think I asked the sir that last week what we did in the last class. So yesterday he taught something and also he did some problems. So I plan to do few more problems in the session also, so that it will be useful to us. I think maybe a couple of weeks we may have an exam, CSR, I think. So it is a kind of practice for you. Let me share the screen.
It's not seen.
Yeah, just a moment. It's loaded. So now what about, could you see the screen? Yes or no? Can you be able to see?
Yeah,
the screen?
we are able to see. We are able to see.
Okay, fine. So I hope all of you have learned the particle linear box and harmonic oscillator problem. Maybe in this course or maybe your PG course, and also some basic rules of this game, the quantum game. So let us start from the first problem. So please read the problem here. The wave function of a particle is given by the psi is equal to 1 by root 2 phi naught plus I phi 1, where phi naught and phi 1 are the normalized eigenfunctions with the energies E naught and E 1, corresponding to the ground state and first excited state respectively. So they have given a superposition of eigenfunction phi naught and phi 1. It's a normalized eigenfunction. So they ask to calculate the expectation value of the Hamiltonian in the state set. Right? Okay. So any clarification in the question? I hope all of you understand the question, right? Okay. So the main difference in if we compare with classical physics, the state right? The state of a system, right? So in classical physics or classical mechanics and quantum mechanics, so the state are characterized by what? In classical mechanics, the state of system characterized by, can somebody reply?
Sir, momentum, position and momentum, sir.
So the position and moment. So if I give you this pair of variable, the value of this variable, then everything is fixed. You can calculate. R and T. So provided the initial conditions and the what is the force are acting on the object, you can be able to calculate the future trajectory. In quantum physics, the state is represented by psi R naught, right? And here, for corresponding R value, for corresponding T value, there exists some energy. Energy can be zero. Suppose if the momentum is zero and the R is the origin, you can choose energy will be zero. But what I mean is, energy is always, there exists some value of energy for given R1. Is it true for psi? For any psi, there exists a unique value or well-defined value for psi.
No, sir.
Is it true?
Hello, sir. What is the question, sir?
The question is, I'm asking for a given R and P in classical physics, we can define a unique energy, the energy value. For a given psi, is it possible to define a unique energy value?
Sir, for stationary state is possible, sir. Like if we have a
Pardon?
bound state for stationary states.
Yeah. So yes, that's a very important point, right? So suppose if psi is a eigenstate of Hamiltonian, then this has a unique value. Suppose this psi is a superposition of the eigenstate of Hamiltonian, then if I measure the Hamiltonian on this state psi, I will not get some value for this psi. I will get one of the value which is corresponding with the superposition of eigenstates. So there is no correspondence between psi and energy. That's a very, very important right here, but it is not true in the case of classical. So no one-to-one energy value website, right? So in this case, they have mentioned clearly the psi is equal to 1/√2 pi naught plus I pi 1. So if I measure H on phi, there are two possibilities. I may get V naught or V. I will. So usually the students used to think if I measure on phi, so what they are corresponding. No, that's I will present. What is the typical thought process? Phi H I say so E naught phi naught and H acting on phi 1 will give you E1 phi 1. Then what they will conclude immediately, if H acting on phi, sorry, H acting on phi 1 psi, they may conclude that we get E1 plus E2, or E0 plus E1. So that is the typical misconception that the students are doing, taking part of that course. So this is not, so it is not true for quantum physics, but it is true for classical, right? If I have a electric field E1, I have another electric field E2. Then if at a given point, if I have E1 and E2, then the total electric field will be E1 plus E2. If we measure electric field, it is a combination of E1 and E2. But in quantum physics, only the states get added, but not the eigenvalues. So state can add, right? State can superpose, but the eigenvalues will not superpose. That's very important. In quantum physics, states can superpose, but not that's very good. Okay. So now, what is the next procedure? We need to find what is the, I think, on the expectation value. We have asked to find out the expectation value of Hamilton. So what is the formula now? Since they have given everything, the direct notation, just straightforward. Okay. Right? But when you do any calculation in quantum physics, you have to first check, right? In our, usually we do in experiment in laboratory, you are going to touch some, are going to use some instrument. What you should do before you use the instrument, you have to check whether the instrument is working or not, right? Then only you can do the experiment. Similarly, before doing any calculation on quantum physics, the first step is check whether the given checkpoint is size is normalized. Just tell me, in this case, I normalized or not. So I have given psi 1 by root 2 phi naught plus I phi 1. So this is a given wave function. Is it normalized or not normalized?
Not normalized.
So here, what is the condition? The general condition is psi is equal to C1 mod square psi given C1 phi naught C1 C2 C2 like that. Then C1 mod square C2 mod square up to Cn mod square is equal to 1. This is the normalization condition. So if you use this case, we have a 1 by root 2 the whole square plus I minus I, because it's a C mod square, right? So if you add it, you may get, I think, 3 by 2, which is really not equal to 1. Okay. So to make it normalize what? To make normalize. So to make the function normalizable. So we have to multiply by 1 by root n, right? Here n is equal to. So we have to multiply everywhere by root 1 by root n. So which means we have psi is equal to root 2 by 3, 1 by 2 by naught plus root 2 by 3 by 5. Isn't it? Am I correct? I hope all of you are following, right? Is it okay? Any clarification?
Yes, sir.
So now this is further. I have 1 by root 3 pi naught plus root 2 by 3. Now normalized wave function. So once if I have normalized wave function, now it's straightforward. Use the formula which is equal to of course whenever you have this kind of there is another formula that I think you may aware. Can anybody say what is the next step in this case?
The sum over probability times the eigenvalue.
So the coefficient square times lambda 1 square lambda 2. So what is lambda 1 here? Lambda 1 is the eigenvalue of phi corresponding to phi state phi naught. Lambda, oh, I think maybe I write lambda naught and lambda. Yes, the notation is a little bit start from the naught. So now you have C naught, E naught, C1 naught square. That's only two state. So what is C naught? So here it is the 1 by 3 E naught plus C1 2 by 3. So this is the expectation value of. So what is the option here? Yeah. So option D. So E naught by 3 plus 2 by 3 E. I think this is the one CSR problem. You remember CSR or next somewhere I took. They have taken whole question option. Okay, so let us go to next problem. Please read the question. What is the dimension of h cross by I, dou psi by dou x, where psi is the wave function in 2 dimensions? So they have given a operator h cross by I, dou psi by dou x, where psi is a wave function of 2 dimensions. So can somebody suggest how to proceed? Okay, let me ask the first simple question. Does psi have a wave function? So does psi have a dimension?
Yes, sir.
So everyone agree that so Psi has a dimension, right? So if
Yes, sir.
if yes, what is the dimension?
1 over root over of length. It's length to the power minus half.
Pardon?
Length to the power minus half.
So it is the as said. So psi will be 1 by L power. This is the dimension. Provided psi is 1 dimension. Suppose if psi is a 2 dimension, I have x comma y. What will be the dimension of psi? Because they have given a 2-dimensional wave function, right? So what will be the dimension of psi of x comma y? Suppose if I have a 3 dimension.
So in 2 dimension 1 over L and in 3 dimension 1 over L over L to the power 3 by
So
2.
yeah, so 1 by L. So anybody having doubt regarding this particular, this is a fundamental point. Yes, some of you may not know this, or if any have any clarification on this result. This is clear to everyone.
Can you explain, sir?
Yes, tell me.
Can you explain how this came?
Yeah, okay. So that's what. So we should first of all, how this came. Let us understand a simple argument. Everyone knows that integration over psi star psi dx has to, right? I mean, maybe little clear I will write. Integration over psi star of x, psi of x, x is equal to, what is this condition? It is a normalization condition. Okay. So in the right hand side, no dimension, purely number. But in the left hand side, we have a dx. What is the dimension of dx? Length, right? The dimension of dx will be length. Now I have a psi star psi of x. So to cancel, remember, right hand side I have no dimension, but left hand side I have a dimension of dx. To remove this L, so I have to, then what I have to have? The psi of x should have 1 by root L, and that is yes, 1 by root L. Then only, so what I mean, so it has to have, so then what happens now? Automatically, this root L becomes L, so 1 by L, so cancels. So no dimension. This is for 1 dimension. Suppose if I have a dx dy 2 dimension, it will be 1 by L, 1 by L. That's what he told, right? So in general, I'll write. In general, for d dimension, n number of particles right as the dimension of 1 by n power. So we have let us first for one particle, then we can look at the dimension. So will be n power n by 2. This is what we should like. So if it is a d is equal to 1, L power 1 by 2. If d is equal to 2, 2 by 2 is L. If d is equal to 3, 3 dimension is be L power 3 by 2. So similarly, for suppose if I have a two particles, then what will happen? We have to again use this normalization condition. Psi 1 mass square, psi 2 mass square, dx1, dx2. Right? So you have to keep on enumerate each and every wave function and find out it. So now let us come to the question. So we get to find out the h plus I rho psi by. So we should find out dimension of h plus, dimension of rho by rho x, and dimension of. So they mentioned it's a 2 dimension. So what is the dimension of h plus?
So energy times
Enappa solunga, tell me.
energy and time. Energy times time.
Yeah.
Joule second.
Yeah, joule second. Of course, that's what you said is a unit, but anyway, let me write. So dimension is different. So you are telling a unit, right? Joule second. Okay, fine. Let me. Okay. So joule second. What is the unit for this dou by dou x?
Meter inverse.
1 by m. And dimension of this, that's how we have seen here. It is a 1 by. Correct? 1 by m. This is clear. So we have now joule second meter minus 2. But I think they have expressed in terms of, look at the question. They have expressed in terms of kilogram second and meter. So let me rewrite joule. What is the joule in terms of kilogram? Kilogram meter minus 1. I think joule is equal to kilogram meter square minus z power minus 2, right? Will you agree this? Kilogram meter. Okay, so now substitute. So the dimension in the place of joule, kilogram meter square minus 2. Yes, meter power. So this turn out to be kilogram. This meter cancels. We have a yes. Having some meter everywhere. Yes, option kilogram second minus 1. So option B. So any clarification? I hope any doubt in this calculation. So this kind of question will again be asked in this any competitive exam, either GIST or GATE or NET. So the more in a different combination they will give in quantum mechanics, you should be able to get the unit or dimension. Shall I go to next question? Any clarification?
Clear, sir.
Okay. Let's read the third question. So we have a particle in one dimension potential that satisfies the potential V of x is equal to V of minus x. It implies the potential energy is even function. And let psi naught and psi 1 denote the ground and first excited states respectively. So psi naught is the ground state and psi 1 is the state. So they have given psi is equal to alpha naught psi 1 plus alpha 1 psi 1 be a normalized state. So psi is also normalized state with alpha 1 alpha 2 being a real constant. The expectation value of position operator x in the state set. So what are the information they have given here? Information 1. V of x is equal to V of minus x. Then information 2. Another. Psi naught. Psi 1. Then third. Psi is normalized. And fourth. Alpha naught. Alpha 1. So four information are given in the question. So we should use whenever you try to solve a given problem, you have to first, as much as possible, information you have to pull out from the question. Every information is some way or other way helpful and make you to solve quickly. So that is the trick. Okay. So what they have asked now, they have asked to find out the expectation value of so let me is equal to psi x. And what is the effect of or what is the consequence of information 1 in the state? We have a potential energy V of x is equal to, so it's an even function, right? It's an even. Whenever the potential energy is even function, then what is the effect of this property on the eigenstate or stationary state? What is the effect? What is the consequence of V of x?
So the eigenstates have definite parity.
Pardon? What tell me?
But the eigenstates have definite parity.
Yeah. So the eigenstates will be important. So this is an important property. So the eigenstate are either even or So it's a much more very nice property. No, it's only true if V of x is even function. So in general, the ground state even first state on like that it goes. Keep on even on, even on, even on like that it goes. So it means it implies psi naught is even, psi 1 is not. So now let us come to our question. Mod x is equal to psi. So please write here. What is the bra psi? So get psi is already given. Get psi is alpha. What is it? Alpha naught psi naught plus alpha 1 psi 1. The bra psi is equal to. So they have mentioned clearly alpha naught, alpha 1 real constant. So we'll get psi naught plus alpha 1. Because there is no alpha naught star, alpha 1 star, because they mentioned is the real function. Now let us write here straight away. This alpha naught psi 1 plus alpha 1. This is the first fellow. Then we have a x. Then we have the alpha naught psi naught plus alpha 1 psi. Second term. So now it's normal straightforward multiplication. You take this. So the first term we have equal to alpha naught square psi naught x psi naught plus alpha naught alpha 1 psi naught x psi 1 plus alpha 1 alpha naught psi 1 x psi naught plus alpha 1 square psi 1 x. Is this clear to everyone? Just straightforward. Alpha naught psi naught this side and x into alpha naught psi naught. So alpha naught psi naught psi alpha 1 psi 1. So just normal multiplication. So now we have to use the next information. Remember, we need to evaluate what is this value, what is this, what is this, what is the nature of value, right? This is basically it is in terms of integration. So here let us try to do this. Psi naught x psi naught. So already we know this is E1, this is E1, this is R. Then what is this fellow overall?
Also,
E1 R E1. So it will be R. So we will get the first term becomes 0. Then similarly, let us do this psi 1 x psi naught. This is R, this is R, and this is E. So this will be even. Okay. So it will not be 0. So this case is psi 1 is psi 1. Again, this is R again. So overall R function. So which means what? It is integration R. So without going for any other straightforward thing, so by just having the property, we conclude that this will be 0. This is 0. So we have now only this this fellow and this fellow. So we have this check whether we have this term in the equation. Yeah. So here look at the option B. Alpha naught alpha 1 psi naught x psi 1 plus psi 1 x psi 1. Yes, we have a option. So the answer is alpha naught alpha 1 psi naught x psi 1 plus psi 1. Is this clear to everyone?
Yes, sir.
So this is the option. Okay. So please read the question. This is the, I think, 2018 or 19 question. Yes, question. Did you read it? A particle of mass m and energy E greater than 0 in one dimension is scattered by potential shown below. So I have a particle having energy is greater than 0, which is a scattering problem, right? It's coming from, and just look at, it is not a kind of which what we have in our regular quantum course. I know we have a very rectangular potential barrier, finite potential barrier. It's not really rectangle, it's a kind of, it's ramp, right? Slowly it is increasing towards the B, A to B. If the particle was moving from x is equal to minus infinity to plus infinity, which of the following graphs gives the best qualitative representation of the wave function of this particle? Okay, so I think here what they expect you not to solve the problem, but using some property already that you are aware, you should be able to guess this answer. Okay, so now what are the information that we can use? What are the information required for to solve this problem? Yes. So how to approach? Any clue?
So we have to look at the energy difference, like like k is equals to root over 2m times E minus V by H cross square. So E, and first the kinetic energy is like E and potential energy is like minus V1.
Hmm.
So there the K will be like shorter, and the as the ramp decreases, means if the energy difference gets larger, the K, that is the frequency, related to frequency, will increase.
Ah. So frequency increases. So what? How it related to the? I think they have given the wave function. So how it related to the probability or probability amplitude?
So the wavelength of the probability amplitude or wave function will decrease as we move from left to right.
Okay. So yes. Okay. Let me. So this is a again. It's a very nice, very cute question. So first important thing that we should know qualitatively, the probability of finding a particle, right, at a given location is inversely proportional to 1 by gravity. Right? So in a given region, but this is a relative sense. It's not, I'm not talking about absolutely. Let's suppose if I have two regions where one region, the particle has a less kinetic energy compared to the other region, then what will happen? So even just you can agree, we can argue with the classical idea. If a particular region, if particle have a higher kinetic energy, which means it will spend less time because it's higher kinetic energy, or it will move fast. If it move fast means it will spend less time in the given region. So when you do measurement, so it has a less probability, you have a less or small probability to find the particle in a given region where kinetic energy is more. Suppose kinetic energy is less in a given region, then what it means, definitely the particle has a less velocity, it will spend more time on the region. So the probability of finding the particle in a given region where kinetic energy is less is more. So that's why I'm giving a qualitative connection. Probability is inversely proportional to kinetic energy. Right? So if probability, then what is the probability is connected? Psi of R square is R. So it's also it implies the psi is 6. Since the psi R square is somewhat the psi R square is the probability amplitude. So where the probability amplitude is more, kinetic energy will be less. Where the kinetic energy will be more, probability amplitude will be less. So probability will be less. So I can have now again one-to-one connection. So psi of it's also true. The same line of reasoning you can also extend to psi. Of course, I cannot, because psi is in general it's a complex, so I cannot write equivalent to kinetic energy. What I mean is where the wave function is having more value in a given region, the kinetic energy will be less. So that is what I want to convey. So now let us. I think this is the information that you require to calculate or to do this problem. So we have a 3 region, right? From minus infinity to regions. We have a 3 regions. Region 1 from minus infinity to A. Then region 2 from A to B. Region 3 B to Yes. So in the region 1, what is the kinetic energy? E minus V. So let's look at the problem here. In the region 1, from minus infinity to A, the potential is 0, right? It is a 0 potential. So which means it is equal to, so since the potential is 0, kinetic energy constant, right? Constant energy. Then the region 2, kinetic energy will be E minus V. But only thing is, the energy, since the potential is not constant over region 2, we should calculate at A. At A, the kinetic energy will be E minus. Please understand, look at the problem. It is a minus V1. So E minus minus V1. So it will be E plus V1. Then at B, kinetic energy will be E minus minus V2 E plus V2. This is at A, this is at B. So what I can conclude, kinetic energy at A is less than kinetic energy so here again, in this case, in the case of this region, kinetic energy will be E minus V plus T. So now we conclude that in the region 1, kinetic energy is constant. So lambda, Fibroid region 2, kinetic energy is increasing from A to B. This means, but already we know lambda is equal to h by root of 2m ke. So the lambda has to decrease as A goes to B. This is clear. But I mean amplitude, right? Lambda and of course the amplitude. Because I told you already, the kinetic energies keep on increasing. The amplitude also has to decrease as A goes to B. Both has to happen. Okay, this is the region 2. Look at here. So which function matches? In the 4 options, which one matches these two, whatever I have said? One is the wavelength has to be constant over from region A to from region minus infinity to region A. Then from A to B, the amplitude has to decrease, wavelength also has to decrease. Right? So which one matches?
3, sir.
So option, what is option 1? Option 1, what happened? The wavelength decreases, but amplitude is increasing. That is completely logical, right? Because what I told, where the kinetic energy is more, the probability amplitude will be less. The probability of finding particle will be less. So, but here it is what did it happen? It is increasing from A to B, right? So it is the other way. And first case is the wavelength is decreasing, but there's a constant amplitude. Again, that's also not possible. because it has to definitely the probability has to change, right? The probability of the particle in region A to region B. And the fourth one, the amplitude decreasing, but the wavelength is not the same wavelength, right? So definitely the fourth one is also not possible. And only the third one is, so far, third one is matching because till A has a constant wavelength, then from A to B, both its amplitude is decreasing, the wavelength is decreasing. Then from B to infinity, look at again, it has a constant wavelength, but the amplitude is decreased. Why it is so? But what is the energy in the region B to infinity? What is energy in the region 3 from B to infinity?
So E, sir.
Again E, right? So whatever the energy particle having energy E in the region 1, the same energy in the E in the region 3 also, but the wave function is even though the wavelength is same, but the amplitude is very, very small. Right? I hope you understand, right? Why can't it take the same form like from minus infinity to A? If it is same value energy, why can't it take the same shape what it has in the region minus infinity to A?
So there's a probability of reflection, sir.
Yes. So a very important point, they mentioned clearly it is the particle of mass m energy is scattered, right? So which means when the particle is approaching from minus infinity to A, right? For example, assume I have a 10 particles which is coming, and there may be a finite probability to get reflected at the point A. So in the region 3, there is no reflection. So only transmission. There's nobody is to reflect back. So definitely only in the whole bunch of particle, only the remaining only can travel in the region B. So definitely the amplitude will be less, even though the constant amplitude, but it is a less amplitude. So the reflection reduce the amplitude. That's a very important. So region 2, region 3. Only reflection, sorry, only transmission. No. So amplitude is less compared with, so option without solving Schrodinger equation, by just using some the important properties, we could be able to use that, or we could be able to reduce that. Yes. So please go through the question 4. Of course, any clarification in the previous question? Any clarification? In fact, I can suggest if you want to understand this kind of the wave function behavior, a qualitative behavior of wave function in a given potential, there is a nice book we can read. Very nice. This is the one book. This is the one. The second one is quantum physics. So both have this kind of the how the curvature of wave function will change when you go from one region to other region. How, in fact, I think this problem is straight away taken from AP French. I remember correctly, I think there is a exercise problem like this. I remember. So we can try to refer those books to understand further. Okay. So please go through the question 4. So they have given X operator and B operator, the coordinate and momentum of satisfying the canonical commutation relation x comma p is equal to I in natural units. Then the commutator x comma p e power minus 2. So they are asking to find out the commutator. This is just a question. So usually we do in our normal course, we do like no x comma p square or x square comma p or square comma p square. These are very familiar, right? But what they have asked here, x comma p e power minus. This is what we have to find. And we are asking to check the total x comma is I. So, as usual, let us use this rule. There is a famous operator rule. A comma B C is equal to A comma B C plus B B comma C. I hope all of you are aware of this rule. We have to apply this rule here. We have now x comma p e power minus p is equal to x comma p e power minus p plus p into x comma e power minus. And the first term is very trivial, right? X comma p is nothing but what? This is nothing but I, because the given mentioned here, x comma p is equal to I. But we need to only evaluate x comma e power minus. X comma e power. So let us do in a direct way. X comma. So expand this e power minus p in terms of the regular series. So what you will get? Can somebody assist me? What is e power minus p in terms of series? What is e power minus x? The series expansion. What is the series expansion?
Sir, identity minus p plus p square the factorial to minus p cube the factorial to.
Yeah. So I think everyone has to get clear idea about this. 1 minus x plus x square by 2 factorial minus x 2 by 3 like that it goes. This is a series expansion of any exponential. So now do that. This is also true for operator 1 minus. Yes, that's what I p 1 minus p plus p square by 2 factorial minus p cube by 3 factorial. It goes like this. So this is the now to just expand. I have here x comma 1 minus x comma 1 minus x comma p plus x comma p square by 2 minus x comma p cube by 3 factorial. So what is x comma 1? The commutator of operator with the number is always 0 minus or identity operator. Here I mean it's identity operator, right? I minus. What is x comma p? I. They mentioned clearly it is I. Then x comma p square, right? It is a 1 by 2. What is x comma p square?
2i.
2i. I hope all of you know why he said Devan says it's x comma p square is equal to. So please understand x comma p square is equal to 2 times of I. Suppose we have x square comma p, 2i times. So these are all some basic things you should know. Similarly, what is x comma p cube? It is a 1 by 3 factorial 3 into I p square. Right? Goes like this. So now we have here minus I plus IP, then minus Roma, there is a 3 factorial, so it will be I p square by 2, then plus I p cube by 3, like that it goes. So this is x comma p minus 1, x comma e power minus 1. So now there is a what is our original expression? We need to find, look at the previous case. Our original thing is p into x comma e power minus. Already we have I into e power minus p plus. Now we have to substitute in the place of second term x comma e power minus p. So p into x comma e power minus p. So right, p into e power minus I plus IP minus IP square by 2 plus IP cube by 3. Now what you do, you take a minus I common, or maybe you can include the minus IP. We have now 1 minus P plus P square by 2 plus P cube by 3 2 factorial. It is a 3 factorial. Just 4 cancels, then 3 factorial. So now what is again this? This is again. This is again. So we have now P into x e power minus P is equal to e power minus P. What? So the original expression, the first page, x comma e power. So we have now x into e power minus p I into e power minus p minus I into e power minus p. So this is I e power minus p common. One minus. This is the I into. We have this option. This is option B. I into 1 minus p. Option. In fact, look at here. Since p and e power minus p is commuting, right? Here they are same function. They become the function of p. So that's why I take common. Suppose if I into this e power minus x means you cannot do it without capacity. So when you do this manipulation, quantum mechanical, these are all operators. The order, you have to always keep track of the order. You should not lose. Otherwise, what will happen? Somebody will take one is common, other is common. So that order, the multiplicative order is very, very important. So this is the another information I want to mention. In fact, this same thing we can do it very quickly. There is a nice identity. Suppose we have a, they say method 2. Suppose if we have a x into f of p, then we have a IH cross df by. Similarly, if we have f of x into p, we have again IH cross df by dx. So if we apply here, I have now x into p e power minus p. So I am writing already since the first one is x comma p e power minus p, and second one is p into x comma e power minus p. So straight away I e power minus p plus p into x comma e power minus p is we use because the second fellow will be I into to differentiate this e power, I have a minus e power minus. So now straightforward I will be I into e power minus p. Straightforward. So I think you should know both, right? Because sometimes you may not be able to use this property, and so better you should know at least once how we say or how we use or how we manipulate the exponential operator in one of these. Either you can use the direct method or this. It's also a nice property that you can verify. Some books are mentioning. So any clarification? So Just look at this problem. Maybe I'll end with this problem. Maybe just quickly read this. A ball bounces off Earth. You are asked to solve this quantum mechanically, assuming that Earth is an infinitely hard sphere. Consider the surface of the Earth as the origin, implying that V of 0 is infinity and the linear potential is 0. Because we know, right, it's a linear potential minus mgx for x greater than 0. Which of the following wave function is physically admissible for this problem? It is possible. So we have a Earth, right? It is say it is the x is equal to 0 and x v is equal to minus mgx as we go on. And here it will be v of 0 is infinity. So what? Any guess? Or any clue? So first one is, remember, what is information one? Information one is the potential is infinity at x is equal to 0, which means whenever potential is infinity, assuming at x is at x is equal to some x naught, if p of x is equal to infinity, it means psi of x is equal to x naught and x less than x naught has to be 0, right? The probability amplitude or the wave function has to be 0 at where the potential becomes infinite. Yes, we cannot cross further, right? So that is the first point, right? The wave function has to be 0. Otherwise, if we pay non-zero means what? Then we cannot match with the wave function in this upper region and lower region. So this is a starting point. The wave function has to be vanish at, in this case, where the x naught. In this case, x naught is equal to 0. So at x naught, v of the psi of x is equal to 0 has to be 0. That's the first property. The first kind of deduction. So which one matches with this? Which one matches with this? A, B, C, D. Either one match. Which one match with this conclusion?
B and C.
So option B, option C is matched. Remember, option A. Option A and option D is not matching. Because option A, when you substitute x is equal to 0, psi becomes infinity. That is itself not possible, right? Because I cannot go to infinity. Then the second one, the option D, when you substitute x is equal to 0, psi becomes a constant value, some A. That's also not possible because I told you first go to 0. So option A, option D is ruled out. Then we have option B and option C. So what is the point? Look at in the option, what is the second point? Psi has to go to 0 as x goes to infinity. That's a basic for any what we say, any non-decay problem, because here the particle is not going to decay anywhere, or going to create, somebody is not going to create the particle or going to decay the particle. So the only possibility is psi of x goes to 0 as x goes to. So now check whether option B, option C matches with this. When you substitute x is equal to infinity, what will happen to option C?
Blow up, sir.
See, option C, psi goes to infinity as x goes to infinity. So option C is also not possible. So the only place is in substitute x is equal to 0, psi goes to 0. In substitute x is equal to infinity, so option B, the only possible wave function is. So this will match with both. Of course, really this problem is one of the little advanced level problem. You can solve this, you will get some. Usually we are not doing this kind of problem in postgraduate, right? We'll do particle in a box, we'll do finite potential barrier, different potential barrier, and free particle and harmonic oscillator and hydrogen atom. But I think it's very rare to do this particle moving in a ramp potential. V of x is equal to proportional to x. So in fact, we can find some good books. So if you solve this, we'll get a Airy functions as their eigenstate. So non-standard functions. Usually we will not get any exponential, or we will not get any sinusoidal. We will get Airy function. So this also a solved problem. But the only thing is it will not a trivial. It's a non-trivial problem. Okay. So any clarification? Any doubt? So I just. Okay, so if you have any questions, you can get some, can have, but otherwise we will close.
So anybody has any point?
Did you learn something today?
Yes, sir.
Yes, sir.
In that case, shall we close then?
Yes, yeah.
Okay then. So thanks to
Okay, thank
Professor
you.
Thank you, sir.
Joseph Prabhakar.
Thank you.
Thank
Thank you, sir.
and good night to all.
Thank you.
Good night, sir.